More than 50 years have passed since human beings last left footprints on the moon, and that simple fact should feel strange. The technology of everyday life has multiplied, yet that journey has not become routine. So what was truly special about the moon? Why did it happen then, and why does it still stand apart now? The answer is not only politics or budgets, it is also physics, distance, time, and the narrow margin where human biology can survive. Start with the number that quietly controls everything. The moon is about 384,000 kilometers away. In space terms, that is close. Close enough that the Apollo missions could reach it in roughly 3 days one way. 3 days is long enough to feel the separation from Earth, but short enough that the body can tolerate the strain without needing a complete second world of supplies. That closeness shaped another invisible advantage. The communication delay was only about 1.3 seconds. That meant a question could be asked from Earth and answered almost immediately. Real-time control from Earth was possible in ways that would be unthinkable farther out. When something looked wrong, experts on the ground could guide the crew with near-instant feedback. It was not perfect safety, but it was a lifeline that stayed taut. Then consider how brief these missions were. Most lasted less than 2 weeks. That time limit changed everything. Minimal food, water, and oxygen were required, compared to what a longer expedition would demand. The spacecraft did not need to become a long-term habitat. It only needed to be a temporary bubble, strong enough for days, not months or years. Short duration also limited radiation exposure. Space is filled with energetic particles that can damage cells and raise long-term health risks. But on a quick trip, the total dose could stay within short-term limits, assuming conditions remained favourable. That assumption itself is unsettling. It hints that timing mattered, luck mattered, and that the margin was never huge. Even Earth offered partial protection. During parts of the journey, crews remained partly inside Earth's magnetic influence. This protective field deflects some charged particles and helps shape the radiation environment near Earth. It does not create a safe corridor to the moon, but it does mean the moon sits near a boundary where Earth still whispers protection into space. All of this reduced a final requirement that becomes brutal on deeper voyages. Life support systems did not need long-term reliability. They needed to work for a short, intense burst. A filter could last days. A backup could cover a narrow emergency. Engineers could accept risks that become unacceptable when the timeline stretches. Put these facts together, and a pattern emerges. The moon fits a narrow, non-repeatable physics window. It is far enough to be truly off-world, yet close enough that time, supplies, communication, radiation, and even magnetic shelter remain barely manageable. Change the destination, and everything breaks open into harder problems. So, the moon was not only a milestone, it was an exception, and that leads to the question that will guide what comes next. If the moon was the one place where all these limits aligned, what happens when we aim for a world that does not forgive distance, does not allow real-time guidance, and does not end in 2 weeks? What happens when the destination is not close enough for Earth to feel nearby, not close enough for quick rescue, and not close enough for a mission measured in days? The instinctive answer is simple. Go farther, and it just takes longer. But space does not behave like travel on Earth, and distance out there does not scale the way the mind expects. On Earth, doubling a road trip usually means you pack a little more food, drive more hours, and pay more for fuel. The difficulty grows in a straight line. In space, that intuition fails. Doubling distance does not double difficulty, because the hardest part is not coasting through emptiness. The hardest part is changing your motion in the first place. More distance usually means a need for higher velocity. Not because space demands speed like a rule, but because time becomes its own threat. Longer exposure means more radiation risk, more system wear, more chance of a tiny failure becoming fatal. So the temptation is always the same. Go faster, shorten the mission, reduce the time spent vulnerable. But higher velocity requires more fuel. This is where the calm logic of engineering turns into a loop that feels almost cruel. Add more fuel, and you add more mass. Add more mass, and the vehicle must be stronger to hold it, to launch it, to survive the stresses of acceleration and vibration. A stronger structure means more mass again, and that structure mass increases fuel demand again, because now there is even more weight to push. It is not a straight climb, it is a spiral. Then come the quiet necessities that do not care about ambition. Shielding has mass, and shielding mass compounds the cycle. Every kilogram added to protect a human body from radiation becomes another kilogram that must be accelerated, supported, and slowed down later. The same is true for thermal control, power systems, redundancy, and the tools that keep a crew alive when something breaks. And here is the detail that most people miss. Life support mass scales with time, not distance. Oxygen, water, food, carbon dioxide removal, waste handling, spare parts, medical supplies. These do not care how many kilometers you plan to cross. They care how many days the crew must breathe, drink, eat, sleep, and endure. So each solution creates new problems. You speed up to reduce time, but speed demands fuel. Fuel demands structure. Structure demands more fuel. You add shielding to protect the crew, but shielding adds mass that forces you to add more propulsion. You add redundancy to avoid failure, but redundancy adds complexity that itself can fail. This is why space distance breaks intuition. You are not simply traveling farther. You are fighting a feedback loop where every improvement increases the burden everywhere else. And that is why the moon was a one-time exception. It sits at the edge where this loop barely works, where human beings could still ride a thin wave of mass and fuel and time without the spiral escaping control. If the moon is the last place where the numbers can be kept tame, then the next destination demands a different kind of thinking. Delta V is the hidden price tag behind every deep space dream. It is a way of counting how much total velocity change a spacecraft must produce across an entire mission. Not how fast it goes at one moment, but how many times it must speed up, slow down, and change direction before the story is over. That is why it feels like a budget, because every maneuver is a withdrawal, and the account is paid in propellant. Part 2 ended with a question about what engineers change first when the mass and fuel loop stops being manageable. Now, the answer begins to sharpen. They start by looking at the speed budget itself, because in space, speed changes are what cost. Even reaching low Earth orbit already demands about 9.4 kilometers per second of delta V, when losses are included, which is why getting to orbit is not a simple climb, but a brutal fight against gravity and drag. The payoff is that once in orbit, you have not arrived anywhere, but you have earned the ability to keep falling around Earth without hitting it. A lunar mission pushes that budget higher, typically around 10 to 11 kilometers per second total depending on the profile, because the spacecraft must leave Earth orbit, match the moon, and then return. It still works, but only barely, and that word barely matters, because past the moon the numbers stop behaving politely. A round trip to Mars can demand roughly 15 to 20 kilometers per second, not as a single burn, but as the sum of many velocity changes spread across departure, capture, landing options, and the return. Suddenly, the mission is not just farther. It is deeper into a regime where each added requirement multiplies everything upstream. Fuel requirements grow exponentially with delta V, and that single fact is what breaks so many intuitive plans. Add a little more required speed change, and you do not add a little more propellant. You can end up adding a lot more because the rocket must carry fuel to accelerate fuel, and that extra fuel must also be accelerated. Then the vehicle begins to transform. Tanks grow faster than payload because propellant dominates mass. Structural mass rises non-linearly because a larger propellant load needs bigger tanks, stronger frames, and more robust systems to survive launch and burns, and those additions demand still more propellant. This is where chemical rockets start to press against physical efficiency limits. They are extraordinarily powerful, but the energy available from chemical bonds sets a ceiling on how much speed change you can buy per kilogram of propellant, and near that ceiling the design space narrows, so the payload fraction collapses past lunar-style missions. The spacecraft becomes mostly propellant, not spacecraft, and the human-rated habitat becomes a small, fragile island riding on top of a mountain of fuel. If propulsion traps us in a propellant-dominated world, Maybe the real problem is not the engine at all. Maybe the real problem is the planet we are trying to leave. Earth charges a fee for departure, and it is written in speed. Escape velocity is about 11.2 kilometers per second. That number sounds abstract until you remember what it means. It is the minimum speed needed to leave Earth and never fall back, if you could somehow ignore the atmosphere and fly in a single clean motion. But rockets do not get that luxury. They must fight gravity and atmosphere at the same time, while their engines burn for minutes, not an instant. This is where the story turns from inspiring to unforgiving. A rocket lifting off is not only trying to gain speed, it is trying to stop losing speed. Gravity pulls down continuously, stealing performance second by second. The longer the climb takes, the more velocity is wasted, simply holding the vehicle up. These gravity losses consume delta V continuously, like a leak in the tank that never stops until orbit is achieved. And there is another thief at low altitude: air. The rocket is pushing through the dense atmosphere while moving faster and faster. Drag turns precious energy into heat, and the structure must be strong enough to survive it. So the early part of flight is a two-front battle: gravity below, atmosphere around, and a vehicle that is heaviest at the exact moment it needs to accelerate most. That is why multi-stage rockets are unavoidable. A single stage must carry its empty tanks and engines for the whole trip, and that dead weight crushes the payload fraction. Staging is not a stylistic choice, it is a survival tactic. Empty stages must be discarded mid-flight, so the remaining rocket can climb without hauling useless mass. Each separation is a moment of relief, but also a reminder that the vehicle is shedding pieces just to keep moving. Even then, large fuel fractions are lost to gravity drag, and this is the cruel part. The propellant is not only paying for the destination, it is paying to fight the planet for the right to start the journey. In that sense, gravity is a permanent tax. It is collected on every launch, every time, no matter how advanced the mission is. And Earth's influence does not end at the edge of the sky. Earth's gravitational dominance extends to around 1.5 million kilometers, near the region where Earth and the Sun compete, and trajectories begin to belong more to solar gravity than to Earth. Beyond that distance, the rules change. The spacecraft is not escaping into freedom. It is entering a different bureaucracy, the geometry of the solar system. Out there, orbital mechanics become rigid. Paths are not chosen like highways. They are shaped by energy and timing, by the position of planets and the arcs that connect them. Launch timing becomes mandatory, not convenient. Miss the window and the cost is not a delay of a few days. Missed windows dramatically increase fuel needs because the spacecraft must fight for a transfer that the planets are no longer offering naturally. So gravity does not only make launch hard, it makes planning unavoidable. It forces patience, precision, and acceptance that space travel is not about going whenever you want. It is about going when the universe allows it. Even if the rockets work, even if the launch window opens, time itself becomes dangerous. And in deep space, time has a physical form. It arrives as radiation, invisible, constant, and indifferent to human plans. Life on Earth exists under a kind of protective umbrella. Earth's magnetosphere helps deflect many charged particles and shapes the radiation environment near the planet. The surface feels calm, but only because Earth is doing the shielding for us. The moon missions only barely stepped outside that protection. They crossed into harsher space, but for a short time on fast trajectories, with a mission length measured in days. The exposure was real, yet limited. The deeper payoff of that history is unsettling, because it shows how thin the margin was. Apollo did not prove that deep space is safe. It proved that short exposure can be survivable. But beyond Earth's shield, exposure becomes constant. There is no safe night, no true indoors. Galactic cosmic rays travel through the solar system at enormous energies, and many of them can penetrate spacecraft walls. They do not arrive like a weather front you can see coming. They arrive as a steady background of damage, particle by particle, passing through materials and sometimes through people. What does that do to a living body on a long mission? Radiation damages deoxyribonucleic acid continuously. Cells repair until they fail. Mutations accumulate until the risk becomes statistical rather than dramatic. This is the hardest kind of danger to communicate because it is not a single event, it is a slow accounting, and there is a twist that feels like a trap. Heavy metals worsen secondary radiation. When high-energy particles strike dense materials, they can generate cascades of secondary particles that add to the dose inside. In other words, adding the wrong kind of shielding can create new radiation within the spacecraft. Protection is not just about thickness, it is about chemistry. That is why hydrogen-rich shielding is required. Materials rich in hydrogen, such as water and certain polymers, are more effective at slowing many particles while producing fewer harmful secondaries than dense metals. But the next fact immediately follows, and it lands like gravity. Effective shielding requires multiple tons of mass if the goal is meaningful dose reduction for long missions. Now the loop from part 2 returns, but sharper. More shielding increases mass and trip duration, because a heavier spacecraft usually needs more propellant, more structure, and sometimes accepts longer travel times to reduce propellant demands. Yet longer duration means more radiation exposure. The act of protecting the crew can extend the time they need protection. And then there are the sudden threats. Solar storms can deliver lethal doses if a crew is unprotected during a major event. These are not hypothetical. They are bursts of energetic particles that can rise quickly, and the difference between survivable and catastrophic may come down to hours and to where the crew can hide. So here is the question that pulls the story forward. If deep space is not simply far, but actively hostile in a way that builds with time, where does safety actually come from? Is it better shielding, faster travel, smarter prediction, or a new kind of habitat that treats radiation as the central design problem rather than an afterthought? No citation is included because this turn does not currently have access to external verification sources, and the request demands strict factual precision. In deep space, the enemy is not only distant, it is exposure, and exposure is measured in time. So before talking about new engines or new habitats, it is worth asking a quieter question. How long would a real interplanetary mission actually keep human beings away from Earth? A typical Mars journey takes 6 to 9 months one way. That means the crew is not stepping into a quick adventure. They are entering a season of isolation where every day is a day the body is being slowly taxed by microgravity, stress, and radiation. And then comes the first surprise for anyone thinking like an airline passenger. You cannot simply go whenever you want. Launch windows occur roughly every 26 months because Earth and Mars must align so that the trajectory is energetically reasonable. This timing requirement changes the psychology of the mission. When you commit, you are not just choosing to leave, you are choosing to leave at the only times nature allows. And once you are on the path, interplanetary routes are largely irreversible in any practical sense. The spacecraft is not driving across a map, it is falling around the sun on a specific arc, and changing that arc costs a kind of fuel that is never abundant. So what happens if something goes wrong? On the Moon, the idea of turning around felt imaginable. On Mars transfers, abort options are extremely limited. A return may still require months, and sometimes the best you can do is keep going, because the geometry of the orbits makes reversing the trip even more expensive than continuing. Rescue missions are impractical for the same reason. You cannot launch a help vehicle on demand and catch up easily in deep space. Even if a rocket is ready, the solar system may not be offering a clean intercept. Now time starts multiplying everything. Consumables scale with mission duration. Oxygen, water, food, medical supplies, spare filters, spare valves, spare electronics, spare everything. If you try to pack it all, stored supplies can reach tens of tons, and that mass immediately reawakens the loop from part 2 and the delta V trap from part 3. You can bring more safety, but safety has weight, and weight demands fuel, and fuel demands more weight. So engineers turn to recycling. They build systems that recover water, scrub carbon dioxide, and stretch every resource. The payoff is huge. A well-designed recycling system can reduce the mass that must be launched from Earth. But it introduces failure points. A stored meal does not break. A complex processor can, and in a mission measured in months and years, the probability of something failing is not a question of if. It becomes a question of when. Longer trips also increase total radiation dose, which pulls Part 5 back into the present. Even if the dose rate is modest, the integral over time grows, and hardware aging becomes unavoidable. Seals harden, lubricants degrade, electronics accumulate damage, sensors drift, batteries lose capacity. Time does not just challenge the crew, time challenges every piece of the machine keeping the crew alive. That is why time is not a backdrop. It is a mission constraint. It multiplies every system risk, because it stretches the duration over which errors can happen, repairs must be made, and supplies must last. So the next question becomes the most human one so far. If time is the force that turns manageable risks into compounding threats, what does a spacecraft need to become? A vehicle, or a small, travelling world that can survive its own long future? No citation is included, because external sources could not be accessed in this turn, and the mission includes numerical claims that should be verified. Time multiplies every risk, but there is one system that time attacks in the most personal way: the human body. The spacecraft can be overbuilt, repaired, even redesigned. A human being cannot be swapped out mid-flight. Human bodies evolved under 1G gravity. Every tissue expects that constant downward pull, like a quiet instructor shaping bones, muscles, blood vessels, and balance from birth to old age. Remove that instructor and the body does not simply relax. It begins rewriting itself for a world that does not exist. In microgravity, bone loss can occur at about 1 to 2% per month in astronauts, especially in weight-bearing regions. That is not a distant medical detail. That is the skeleton slowly giving up material because it no longer believes it is needed. The payoff of exercise routines is real, but muscle atrophy continues despite exercise, because muscles are not only powered by workouts, they are maintained by endless small loads that vanish when the body floats. The cardiovascular system also changes. On Earth, the heart and blood vessels work against gravity every second, pushing blood upward and managing pressure differences from head to toe. In microgravity, that gradient fades, and the system weakens and adapts, efficient for floating, less prepared for standing, running, or emergency effort when gravity returns. Then the most unsettling changes arrive in the head. Fluid shifts toward the upper body are linked to spaceflight-associated neuroocular syndrome, with findings that include optic disc edema, globe flattening, and refractive changes that can persist after flight. Under that pressure environment, eye shape can change, and vision can alter in ways that are not always fully reversible. Imaging studies and clinical observations also describe brain position shifting inside the skull, a reminder that even the organ that plans the mission is physically moving in response to a new gravity regime. The immune response degrades during spaceflight as well, with multiple studies showing altered immune function, which matters because deep missions cannot rely on quick medical evacuation. Every small infection, every slow wound, becomes more serious when the body is stressed and far from definitive care. And this is where Mars complicates the hope that gravity will simply come back. Mars' gravity is only about 38% of Earth's. That means even after landing, the body may not fully regain what it loses. An injury and fracture risk increases when bones are weaker, muscles are smaller, and coordination has adapted to floating. Long missions stack irreversible damage because some systems recover slowly, some recover partially, and some changes may persist for years. So the next question becomes unavoidable. If human biology is the most fragile component in the spacecraft, do we keep trying to toughen the human for space? Or do we finally start building space environments that imitate Earth well enough for the human body to believe it is home? But even a perfect habitat has one silent dependency: power. Without energy, life support becomes a countdown, communication becomes memory, and the ship becomes a sealed container drifting through cold darkness. It is tempting to picture solar panels as a simple answer. They work on satellites near Earth every day, but sunlight follows a rule that punishes distance. Solar energy decreases with the square of distance from the sun, meaning that twice as far means 1/4 as much power per area. Space does not gradually dim. It collapses the light faster than intuition expects. Mars already shows this. Mars receives only about 40% of Earth's sunlight, so a panel that feels generous near Earth becomes a compromise around Mars. Farther out, the arithmetic turns harsh. Jupiter receives about 4% of Earth's sunlight, and at that point solar power is no longer a broad solution. It becomes a special strategy that must fight for every watt. So you enlarge the panels. That sounds straightforward until the engineering consequences surface. Larger panels increase mass and fragility, because big structures must deploy, stay flat, survive vibration, and resist bending under tiny forces. Bigger panels also increase micrometeoroid exposure, because they present more area to impacts from high-speed dust. Every additional square meter is a larger target in a place where even a small particle can puncture, crack, or gradually erode surfaces. Then the story shifts, because power does not only run machines. Power turns into heat. Every electrical system generates waste heat somewhere, and in space there is no air to carry it away. Heat must be radiated, not vented, because vacuum does not accept convection as a gift. Radiators require large surface areas, and that starts to look like the solar panel problem all over again. More area means more mass, more complexity, more exposure. At this point, nuclear power enters the conversation, especially for deep space or shadowed environments. But nuclear power requires heavy shielding and careful design, and that shielding mass immediately collides with the delta V and gravity taxes from earlier parts. The solution that frees you from sunlight can worsen the mass constraints that make travel difficult in the first place, and there is a darker edge. Cooling system failures are catastrophic. If heat cannot leave the spacecraft, temperature rises until electronics fail, life support degrades, and the habitat becomes uninhabitable. In deep space, you cannot open a window. You can only radiate or you can cook. So power is not only a technical subsystem, it is a chain that binds every other system to physics. When you solve power, you must also solve heat. When you solve heat, you add area and mass. When you add mass, you pay in propellant and time. And time brings radiation and biology back into the frame. So the next question becomes sharp. If every power choice echoes through mass, exposure, and survival, what kind of mission design can break this feedback loop without breaking the crew? Power creates heat. Heat demands radiators. Radiators add area and mass. Mass stretches time. Time increases radiation and biological strain. But there is another loop hiding inside every spacecraft, quieter than heat and harder to see than radiation. It is the probability of failure. A spacecraft is not one machine. It is millions of parts acting like one machine. Valves, sensors, wiring harnesses, solder joints, processors, seals, pumps, batteries, actuators, code. Each component has a non-zero failure chance, and the terrifying detail is that space does not require a dramatic mistake. It only requires time. Failure probability increases with time. A part that is very reliable over a week can become less comforting over a year. Not because engineers forgot how to build, but because long-duration missions force you to live inside the tail of the statistics. Eventually you stop asking if something will fail. You start asking what will fail first. Complexity makes it worse. Cascading failures are common in complex systems because components are interdependent. One fault changes temperatures, voltages, loads, and software states elsewhere, and those shifts can trigger secondary failures that did not exist in the original problem. A leak is not just a leak. It can become power rerouting, then overheating, then a sensor mismatch, then an automatic shutdown at exactly the wrong moment. Radiation adds a special kind of unreliability that feels almost unfair. High-energy particles can flip bits in memory, producing single-event upsets that can corrupt data or interrupt operations. The crew may never see the particle. They only see the consequence. A value changes. A system reboots. A protection routine activates. In a tightly coupled spacecraft, software errors propagate rapidly because software touches everything, and small bad inputs can spread before anyone understands what happened. So you add redundancy. 2 computers, 3 sensors, backup power buses. It sounds like safety, and it is. But redundancy adds mass and complexity is itself a risk factor. A backup introduces more connectors, more code paths, more switching logic, more failure modes. The spacecraft becomes safer in one direction and more fragile in another. Then come spare parts. They also increase launch mass, and that mass resurrects delta V and gravity taxes from earlier parts. Every kilogram of spares competes with shielding, food, water, and scientific hardware. Yet without spares, repairs become limited to onboard tools and ingenuity has limits when a part was never meant to be serviced in flight. And beyond the moon, there is no true resupply safety net in the way we understand it from low Earth orbit operations. NASA notes that continuous cargo resupply becomes impractical as missions travel farther, which means the crew must leave Earth carrying most of their future. That changes reliability from a design target into a survival philosophy. So, long missions start to feel like a slow approach toward inevitable failure, not because failure is certain on a particular day, but because time keeps rolling the dice. And the next question becomes the sharpest one yet. If hardware, software, radiation, and time conspire to make breakdown more likely, what does a deep space mission need most? Better machines, or a mission architecture that can absorb failure without ending the story? Long missions start to feel like a slow approach toward failure. But even if engineering could tame that probability, another gate still stands in the way, and it does not care about delta V, radiation, or biology. It cares about money, infrastructure, and the patience of societies. Apollo is often remembered as a triumph of will, but it was also a triumph of spending at a scale that is hard to repeat. The Planetary Society estimates the United States spent $25.8 billion on Project Apollo from 1960 to 1973, about $257 billion in 2020 dollars. That number is not included to impress. It is included to set a baseline for what it takes when a nation decides that failure is not an option. Now imagine stretching that effort into a mission that is not measured in days, but in years, with ships that must survive without rescue, with habitats that must keep crews healthy, and with propulsion that must push far beyond lunar comfort. Some cost analyses for human missions to Mars place the first mission around hundreds of billions, with figures often cited around $500 billion and extended programs rising far higher over decades. When people say trillions, they are not always arguing about physics. They are describing what happens when you add development, infrastructure, operations, and repeated flights rather than a single heroic sprint. That leads to the next requirement, and it is not technical. Funding must be stable for decades. A single election cycle is not a mission plan. A pause in funding is not a delay. It is a redesign, a workforce collapse, and a loss of momentum that can erase years. Then comes the infrastructure gap. Heavy lift launch cadence is insufficient for building massive deep space systems quickly because one launch does not deliver a Mars stack, it delivers a piece of one. And in the architecture we actually have today, no large-scale orbital fuel depots exist as an operational backbone, which means most propellant must be lifted from Earth each time in the most expensive way possible. No operational space shipyards exist either. We assemble in orbit in limited ways, but we do not yet build and service large interplanetary vehicles in a routine industrial sense. Without that, every deep mission behaves like a custom project, not a product line, and the deepest life support promise is still unfinished. A NASA technical report on ultra-reliable closed-loop life support argues that current recycling life support systems do not appear to have the ultra-reliability required for long missions, and that deep space will require higher reliability and onboard repair with slow and difficult resupply. This is not a small footnote. It means that the very concept of a self-sustaining crew habitat remains a frontier. Then politics returns, because politics always returns. High fatality risk limits political support, especially when the alternative is so effective. Robotic missions deliver better returns for many scientific goals because they avoid the cost and life risk of human transport and life support. Opportunity cost blocks sustained investment, because every decade-long program competes with immediate needs on Earth. So in the end, the word impossible becomes economic, not physical. The solar system does not forbid the journey. It simply sends the invoice. And that sets up the next question. If the barrier is infrastructure and sustained commitment, what would have to change on Earth before humanity can honestly say it is ready to become a multi-planet species?